Yeah, so the idea is to model interaction with an artificial agent using a channel, basically transmission through a channel, which is the information theory kind of approach to connecting two random variables. But overall, kind of the difference between this and some of the stuff that we know from controlling generative models is that it's more about influencing a generative agent by finding some mutual information with another data source, rather than a control problem that is conditionally trying to map input to output based on a set of examples. So hopefully it will get a little bit more clear as we go. Now, the motivation for this is kind of to propose this model for influence. So generative models learn probability of some data. So that's kind of what makes it generative. And sequence learning or musical sequences often are modeled in some kind of a autoregressive way. So these are kind of the language models or the predictive models that do continuations. Although you can also do this not only as a decoder, but also as an encoder with in-painting or completion of missing data points. So this is sort of a self-supervised learning, because you basically take part of the signal, and then you have the other part of the signal that serves as the target. So all of these are ways basically to model the data, and because it's done in some kind of a probabilistic way, it becomes a generative model. Now, if we talk about a human interacting with a generative source, or maybe two agents, in the musical case, I think it's natural to think about this as multiple voices or polyphony. Now the question is, do you learn the polyphony together just because we have polyphonic examples, or you have two individual agents, every voice is an agent, and then we want to learn also relations between the voices. But usually when we learn polyphony, we bundle them together into some kind of a joint representation, and then we learn hopefully everything together. The statistics of each voice and the statistics of the relations between the voices. But each one of these tasks, basically continuing a voice or modeling the relation between the voices, is learned by providing a set of examples, and then you basically build a probabilistic model for that specific task. So if you want to do accompaniment, you might want to learn the relation between the melody and the bass. If you want to go the other way around, to create solos given the chord progression, these are all very relevant tasks. What I kind of propose here is less of a well-defined problem. It's more creating communication between two voices. And this model specifically will be using so-called channel capacity, which is a term from information theory. And this channel capacity problem actually is finding sequences that, or basically having one agent pass through a channel to generate a response from another agent. And the goal is to maximize the flow of information, or the amount of communication of one agent with respect to another one. So this is kind of a very generic approach, saying that we don't really want to control something in the way of mapping one sequence to another. We want basically to find a way to maximize some kind of flow of information between the sequences. And if one of the source can be human musician, the input of this channel, the output will be basically the response of the machine, or the other way around. The machine can be the input, and the channel actually creates the responses of the human, and we want to kind of maximize their mutual information. So I know it's kind of still very abstract, but part of the motivation is actually, I would say, comes from ideas that were adopted in UX, basically in user interface or user experience. And they're known as Higgs law, okay, or a specific aspect of this Higgs law is Fitts law. So what Higgs law says is that the time it takes for a person to perform a task is actually logarithmically proportional to the difficulty of the task. Or it's proportional, then let's see how proportional to the complexity of the task. Okay, so we'll talk about where the law comes in. But the idea is that, if you have one option, you respond quickly. You have two options, you respond slower. The more options you have, the more things you have to consider, the longer it takes you to process this. And Fitts law is actually something that, let me kind of switch to the link. Is a specific case where the task was given as tracking a target. Okay, so, and the Fitts law is basically something that tries to give what they call index of difficulty for the task, and the difficulty is proportional to how far you have to move a cursor or your hand, your finger, whatever, to point at the target, divided by the width of the target. Okay, so and this number is supposed to give kind of the difficulty in performing a task, and then from this number, when you divide this by the time it took you to move, okay, this gives kind of the index of performance. And now that kind of led, actually, I mean, I'm kind of just really browsing quickly through this Wikipedia page. I mean, feel free maybe to review this later. I mean, this is kind of interesting points to consider, but the idea is that this measure, okay, was later changed into slightly different law, okay, that gives you this expression, okay? So the index of difficulty, or how much processing is required from a human to perform a task of moving towards some target, okay, has this specific expression. And the reason for looking into this expression, because it kind of seems, or it's written mathematically as the Shannon expression for channel capacity. So that's kind of my way to introduce the idea of channel capacity, that basically it tells you, or it gives you some sort of a model. Okay, if we go now backwards, we could say a task that you have to perform could be seen as some kind of information that has to go through a channel, and that channel has this type of expression, which will now link to so-called signal-to-noise ratio. Okay, so the experiments that the psychologists did to validate this, they're outside of the scope of all the details, how do you adjust and what they did, but let's assume that this is given as some kind of a possible empirical evidence that gives some quantitative evaluation of an interaction task, okay, performing a task. Now, to give like a better example of this thing, okay, I would maybe suggest, and we can kind of do a little pause, just playing around with this app, okay? And the idea is that here's your task. You have to click a button, okay? You have to move and chase this. Okay, now it changes the task, so you can see that the smaller the the smaller the distance and the bigger the target is, okay, the faster and the less error you'll be doing. Okay, now it's harder, right? Let's see when it, no, this is small, so it's hard, maybe it's not. So I'm just kind of playing around with this just to demonstrate, collect some data. At a certain point, I'll stop because it's a fun game. But the whole idea is kind of to demonstrate it collects data, and then it tries to fit it into this log thing. Okay, so what do I do here? Let's see. Okay, so I didn't collect enough data to prove that it actually gives you this regression that matches this this empirical equation. But I think at least when playing with this, it kind of gives you the idea that there are some tasks that are easier, and of course, the bigger the dot is and the closer they are, the faster you can run this model. And when it goes to like, this is a hard task, right? I'm making more errors and I'm performing slower. Okay, so again, I don't think I'm connecting here enough dots to convince you that the theory here actually supports this kind of a log equation. But you can see that this time of milliseconds over effective ID. So the effective ID is this expression, okay? And this is kind of the attempt to kind of validate this theory. So regardless of whether you're convinced that this theory is correct or not, I think it's pretty clear that there are tasks, that easy tasks are faster to perform and more difficult tasks are slower to perform because it requires more effort. And or if you think about this as some kind of information processing task, it takes more computational needs. Okay, so keeping this as an overall motivation, the next step is kind of to claim that this sort of notational similarity actually has some kind of an insight or meaning that could be relating this to information theory. So this is an expression, the lower one, for channel capacity of a Gaussian channel where you transmit a signal through a channel that adds noise. So this is basically an additive channel. So let me kind of, again, use some of the Wikipedia for this. So here is this expression that was derived independently, and they're not related. Really, what happened was that, this index of difficulty, when it was rewritten in this way, it reminded of the channel capacity theorem or equation. So what is the channel capacity? Basically, it tells you that if you have a communication channel, okay, with certain bandwidth, okay, you can measure this in frequency, bandwidth in hertz, okay, you have a signal that you want to send through this channel that has certain energy or power, okay, and during the transmission there is some added noise. So this expression basically tells you how many bits per second you can deliver through such a channel, and you have this log of 1 plus signal over noise expression times the bandwidth. Now, for us, doing a lot of signal processing, everybody's familiar with other expression, which is really the Nyquist rate that tells us that, okay, you have some sampling frequency. Okay, so you can sample in a rate that is less than twice the bandwidth. That's kind of the Nyquist thing, right? So you have to sample the pulse frequency, okay, in pulses per second, and B is the bandwidth, right? So you have to sample twice the bandwidth in order to be able to transmit or sample not more than 2B, okay? And then we can also think about how many levels, if you think now about not only the sampling rate, but also the quantization, okay? So if you are quantizing something between minus A plus A volts, right, and your quantization step is plus minus V, is delta V, that's how many levels you can have, right? 1 plus A divided by delta V. So in this ideal sampling, if you think just about transmitting a signal in a digital way, where you sample this at FP, and you quantize this with steps of delta V, this is really the rate of transmitting through this channel, right? That's kind of doesn't require any information theory. It's really the FP, the number of sampling frequency times the number of bits that you transmit for every sample, because this is basically quantized. Okay, so this basically tells us that the rate is 2B, F has to be less than 2B plus log M. So now, trying to see this equivalence between these things, you can say that comparing the Shannon capacity to the thing that we derived before, which is just straightforward sampling times number of bits per sample, you see that that kind of gives us this relation. So you can see that there is some kind of a different point of view here that really tells us that, because these are powers, really M, right, is really the ratio of the amplitudes, right? So the square root effectively converts the power ratio back to voltage ratio. So the number of levels is approximately proportional to the ratio of signal RMS amplitude to noise standard deviation. So this is not a proof of the Shannon capacity law, but it kind of gives a pretty evident relation in the ideal case of just sampling and passing sample by sample as coded in bits. So yeah, so there's a little disclaimer about that it should not be interpreted to mean that M pulse levels can be literally sent without any confusion. More levels are needed, whatever. But you can see this analogy. So maybe check out this page later. So what is this channel capacity thing? Okay, so channel capacity is in the information theory sense or the statistical sense, is defined in a probabilistic way. Okay, so we kind of like started with questions of a load or difficulty of the task, and then we showed that this looks a little bit like trying to transmit that many bits, and that many bits could be also thought as rate of symbols and the number of bits per symbol that we transmit. But in the information theory sense, channel capacity is really described as mapping between messages and decoded messages that go through some kind of a channel that is described as a conditional probability. So you have X that goes into a channel. That channel is characterized as conditional probability of X given Y. So for every X, you might have different Ys that will be generated, but they're conditioned on X. So this is not one-to-one mapping. This is probabilistic mapping. So then you get these Ys that will be decoded back into something that is the message. So there's the encoder decoder, but the channel itself is really mapping between X and Y. Okay. Now, the idea of channel capacity, and that's kind of what what Shannon defined was, well, once we have X and Y, we have the joint probability, we have the conditional probability, and we have the source probability, right? So basically, depending on the input, you have the prior, the probability of input to the channel, you have the channel itself that takes X and maps it to slightly different data point. And if you use Bayes' law, you can say that this is their joint probability. So you have basically joint probability in input and output. And I'll remind in a second some definitions of mutual information. Actually, I think it's actually nice to see it here. Mutual information is really considering the entropies or the uncertainty of X, uncertainty of Y, and their intersection. So their intersection is the mutual information. Okay. So channel capacity is really the maximal mutual information or the maximal overlap between X and Y, where you are free to choose your input. Okay, so over all possible inputs, okay, there is some type of encoding or some distribution over the input to the channel that will give you the most effective, or give you the Y that has most information about X. And in some sense, that's the best way you could transmit through the channel, because the problem is with the channel is that it's lossy in the sense that it adds errors. Okay, it's not lossy, it adds errors, to be more precise about error correction stuff. So the error is really represented by this probability. So in some sense, you'll minimize the errors if you find the best input so it has most information to the output. Okay, and we'll see in a second what it means. And for that best sequence that we don't know it, but we can search for it, that supremum, that maximum mutual information input and output, is the channel capacity. Okay, and then there are all kinds of rules about channel capacity. Now, for Gaussian additive noise, we can actually now link this expression, which is the maximum over, or the supremum over, mutual information with X and Y, to the Gaussian noise to prove this expression. Okay, so I'm going here a little bit through kind of information theory things. Okay, just kind of to convince you that this relation between difficulty of a task and a channel might have some powerful intuition, let's say. Okay, so here is the proof of the Gaussian channel, and the reason I'm going through this is really kind of just to show you, or give a little bit more of the mathematical side of that intuition. This is from the information theory book by Thomas and Cover. So this is the definition of mutual information. Okay, it's actually the entropy of one of the variables minus the conditional entropy of the other one. Okay, and this is the channel. The channel says I input something into the channel. That's my original encoding X. There is some noise added, and then it generates Y. Okay, so I'll go very quickly through this whole thing. So there's the definition. Y itself is X plus Z, right? So this is it, given X. So because X given X doesn't add any uncertainty, there is no, so we can basically eliminate this. The only entropy here is HZ given X. And because Z itself doesn't depend on X, that's just a random noise added. What you see is that the mutual information between X and Y is really the information of X, which is represented as the entropy of Y, right? Sorry, the mutual information X and Y is the uncertainty about, or the entropy of Y of the output minus the entropy of the noise, HZ. Okay. Now, for further proof, sorry, you need to believe me that this is the entropy of a Gaussian distribution. Okay, it's log of the probability. That's where the variance comes in. The n is the energy of the noise, And if you follow all these equations, you get to this expression, okay? So you have the log of the y, which is the power of the signal, or the variance of x plus the variance of the noise minus the entropy of the noise itself. And very nicely, you come up to this expression. So I think the graphical interpretation is the most telling. So what it actually means is that, let's say you have a signal, okay, of power p. You add noise, so your total signal is of power p plus n, okay? And if it's n-dimensional, let's say it's n dimensions. If if it's two-dimensional, think about this as a circle, okay? So you have p plus 2. You have n signals, so it's n square root of this, okay? This is the radius of the signal that you transmit, and this is the uncertainty of every error that happens during transmission. So you try to transmit the signal, and then the error bumps it to some other point. So then the most efficient encoding will be something that quantizes your signal to these numbers of levels, where the circle here, the small one, is the variance of the noise, and this is your signal, total signal energy, plus the noise, okay? So this is how much you can pack if you are basically sending something with this energy, but then each signal that you send is little kind of bumped or moved around with this uncertainty. So this is really how many certain levels you can have. So this is kind of the idea of packing a certain amount of information, and the more noise you have, the less information you can pass. Because if you have these little circles bigger, okay, then you can transmit only 2 bits of information, okay, or 1 bit or whatever, okay. The less noise you have, the more bits of information you can transmit. That's kind of the overall motivation, okay. So the more noise you add, the less information you can pass through the channel, and that gives you this expression, okay. So that's kind of the explanation about the concept of capacity. So what I'm kind of now doing is assuming that I convince you there is some motivation of capacity as difficulty of a task in interaction of performing a task. And now we look at the capacity, and this is the definition we showed before, okay. Basically, this is another explanation saying that, okay, what we have is, if we have an input sequence, okay, of n symbols, okay, and then we have outputs y, okay. This is how many possible y outputs you'll have for an x, okay, to the power n of h. Now, for those of you who might have taken information theory, that would be a familiar term. If not, basically that's basically, instead of having 2 to the power of n possible sequences, the entropy itself is this multiplicative factor. So what you have is the total number of possible output sequences is 2 to the power of n entropy of y, okay, and then the total number of possible typical y sequences, we calculated, and now this set is divided into the set of size 2 and h y given x. So that means how many different x sequences you can derive from every y. So the total number of disjoint sets is less than or equal to this difference, okay, which is this expression. So I don't know, for those who kind of like heard about typical sequences and how entropy and the different and the number of codes is related, it might be another way to look at the same explanation. If this is confusing because it introduces too many new terms, just ignore it. But that's kind of another motivation of looking into why this mutual information is really the ratio, okay, the total number of disjoint sets when there is some uncertainty about the output, given that you have some possible typical pairs, okay. So that's why we can send at most 2 to the power of n mutual information number of distinguishable sequences of length n through a channel. Okay. So now let's go a little bit back to the idea of performing a task, okay, that might have a different difficulty, but now we introduce memory, okay? So this is one of the papers that I suggested as reading material, so you know what I meant to talk about. And this is the paper, let me see, I can switch to, what was that? Sorry, this one. Information rate in human during visual-motor tracking, okay? So this is you know, a project that, you know, we're also trying to continue with Alexander Zenon, which, you know, which is kind of motivated by this early paper that they had. And what they were trying to do is kind of extend or generalize this initial Higgs law or Fitts law experiment to tracking of a signal. Okay, so you know, they mentioned the Higgs law here. Okay, I don't know why. Let me remove this search. Okay, so this is their task. Okay, their task is instead of pointing at a random dot where the measure is, you know, how difficult the task is in terms of how far the dots are divided by the size of the bigger the dot is, the easier it is, but you know, the farther it is, it's more difficult. So instead of doing that measure, which is and that mutual information or the channel capacity idea, here you have a task of trying to track uh, with a cursor a signal that shows up on the screen. Okay, so the blue one is the input, and the red one is a person having kind of to move a slider up and down to track that signal. So of course, when it starts, the person doesn't know what the signal is, so it kind of starts having more and more errors. After a while, you actually learn that this is this nice sinusoid, and you can basically start moving your hand up and down. And if you catch nicely the amplitude and the frequency and nothing here happens, you actually don't really need to look at the screen anymore, right? You can just keep on doing this movement and you'll be tracking very nicely the blue curve, which means that this becomes an easy task. Why it's easy? Because you kind of can predict the output based on, you know, on the model that you created in your mind. Okay, but if the movement, if the task, the blue line becomes more erroneous, you know, you have to keep track and keep looking at the curse at the, you know, at the screen. Okay, at the target, and you can see that you know, tracking is also giving you more errors. But another thing that happens is that there becomes more and more delay between what the human manages to do and the or the, you know, the thing that shows on the screen. Okay, so the target versus the tracking response start being delayed. Okay, so that delay is considered as a measure of, you know, the amount of processing that is required. Okay, the more you delay, the less you manage, and of course the error between the two, okay, is kind of a measure of the difficulty of the task. But the only difference between this and the previous task of random dots is that here you can also have some sort of prediction of the signal. I mean, even though this one is pretty erroneous, it still has some model that, you know, you can still kind of predict. Okay, so going back to the slides, in such a case, you know, the model of a channel or, you know, that memory that you have, or the ability to predict something based on the previous things that you learned, is considered kind of a channel with memory or channel with feedback. So what we have here is really the output Y, okay, that depends not only, so the input here is the blue, okay? This is the target, okay? The Y output is your tracking response. Now your tracking response, so the ability or the amount of information that goes between the target, okay, and the target might have long paths. Okay, so X has some length of, here it's L, but it could be from -infinity to this point, okay, to point N. So the information between the past of the target, okay, and your response Y. Here there's also a little delay D because we claim that there's kind of a natural delay in these visual motor experiments. In theory, that D doesn't exist. When you talk about communication channels, there is no like fixed delay. Just this will be the prediction of time N. So the information between the output at the current moment N and the past of the signal up to this current moment, okay? This would be basically the information that now also takes into account the past of the outputs. So this is the feedback, okay? So the samples, in this case, they consider fixed memory K. So the K past samples of your output, you kind of consider them or you take them into account when you try to measure how much information your next sample has with respect to the target. Now, why do we need to do this? Because the output here might depend on your predictions, okay? So it's not only the information that you see, it's not only the data point of the target that now governs your next output, it's also the past of your input, okay? So, oops, okay. Now let's kind of maybe jump forward to kind of ground this into musical motivation. So in our case, basically the idea is, okay, let's say that Y in our case, okay, is it could be one of the agents, either the musician or the human musician or the agent, okay, or it's one of the voices. So now when I'm doing the jump between this and two melodies, okay, I'll be looking into this expression, okay, and we try to motivate this slightly differently. So it's not like tracking, it's tracking in parallel, let's say, okay. In some sense, you have a musician performing something and the improvisation algorithm doing something. Now, if you want to measure how much influence, okay, X, one of the voices has on the next sample, on the output of the second voice, okay, you need to kind of remove the influence of the past of that voice. So if, let's say, I don't know, let's call Y the soprano and X the bass, okay? So if you want to know how much information is passing between, whatever the bass was playing till now to the next note of the soprano, okay, that next note might be listening to the bass, but it also has its own history. It has its own dynamics, okay? Because YN, if there was no bass, would be still generating something in a conditional way, okay? So it has its own melody, it has its own style, which is represented by the past of that signal. So if you want only to measure the influence between the past of the bass and the next decision of the soprano, you have kind of to remove the influence of the past of the soprano. So conditioning in some sense tells you that what you care about is only this information when the past is given. So the past is actually was influencing both X and Y, and now you condition on it, so you don't want to see it, okay? But just kind of to demonstrate or go a little bit one more step, if you go back to this tracking thing, basically for that experiment, and that's the paper that I referred to about the information rate of the visual motor tracking. In their case, they were kind of trying to validate this measure by, well, you have to model the prediction in some way. So they used a Kalman filter to analyze the two sequences, Okay, so basically the task was given to a human. You had different levels of fluctuating target. Okay, and the human has to track it, and depending on how randomized was the target, you could get these curves that we saw before, these signals. And then they kind of try to emulate or model the human tracking behavior as a Kalman filter. So Kalman filter is just a continuous version of some kind of predictive model, okay, where you have states, okay, so you have a prediction that happens inside the filter, okay, and then with this prediction, you kind of predict with these states. So the states have their own prediction, they have their own dynamics, okay. In some sense, these are the hidden states. From them, you derive your prediction of the next thing that you will observe. Okay, that's your prediction. This is your actual observation. Okay, so there is this error happening here, and this error signal basically is fed into the Kalman filter to make the next estimate. So you always estimate your next state based on the observations that you have, or actually the error between the observation and the prediction and the previous state. So the forward, so they have the forward information and the feedback information. The forward information is really the dynamics of the Kalman filter. So it learns the dynamics, but then once it has it, you can measure the flow of information inside the system. Okay, that's what makes the prediction. And then you have the feedback information, which is really just the error between the predictions and the observations. Okay, so what they try to do is compare the tracking lag to the measure of the feedback information. Okay, and the feedback information is this kind of information measure, which basically takes into account or removes the influence of the prediction and just measures the information that is how much the error or the observations influence the state when you actually kind of remove the information that came from the prediction itself. So the hypothesis was the transfer entropy, okay, which is the information of the feedback, okay, is a good marker of the amount of the cognitive resources required by a task, okay, and so here actually they have these measures of forward feedback information, forward information, and they compare this to the different things they measure from the Kalman filter, okay, this and this, okay, and then they show that they have this measure, which is the performance lag. They had to normalize this by this delay that apparently was different for different people. But then they show that actually their theoretical log performance lag, which is basically the difficulty of the performance, performance lag and the feedback information, they actually perform like in this log relation. Okay, so that's kind of claiming, or that was sort of the proof that the transfer entropy is a good marker for the difficulty of that task. Okay, so again, motivation, but kind of presented in mathematical way as a prediction, and a very specific prediction that has a predictive model and the information in the error, the updates that the predictive model was not able to perform. So how is this related to the problem of agent interaction? So in some sense, now we kind of take this idea of the channel and say, we apply this to two interacting agents, okay? And so we kind of think now about, okay, we have two musicians performing, two voices, and they're connected by this invisible channel, okay, where the behavior of one agent is the task for another agent to follow, or maybe the other agent then follows the first one. So there are all these questions: can we quantify which one is the follower, which one is the leader, which direction the information is passing more? So that's kind of one aspect of really analyzing improvisational relation between voices, polyphony, using these tools of measuring the information between the voices. And then the next application is using this to fine-tune or kind of modify the generative properties of one of the voices so that information will be maximized. So in some sense, if we have a generative agent and we have a musician, usually there is very little influence between, what the musician does and the agent. Many times, there is very little. Maybe you can query somehow the agent, so it will maybe improvise something that kind of resembles instant. You can have like, okay, this sound here, or these notes now could kind of give bias towards what the agent generates, but these are kind of like ad hoc mappings, and then the agent has to decide whether it's going to match the incoming signal or its own dynamics. So the same kind of questions exist, but they were not formulated as this kind of noisy channel problem. Now, the generative agent might not be familiar with the music of the human. So there's a task that you need kind of tune or fine-tune the generative properties of the agent to maximize the communication between the two. That's kind of how basically I'm trying to define this problem of agent interaction. And if it's not done immediately during the concert, one of the ideas is that you can have rehearsals as a way to fine-tune the agent. Okay, and the communicative effectiveness, or how well an agent and a human are interacting, could be measured by this mutual information. Okay, and part of the idea is to find a way to keep rehearsing or keep improving the model by measuring mutual information. So maybe as long as you interact with the agent and you have maybe some sessions, and then you go to another session and you see that the mutual information increases, then the interaction improves. And of course, there's this limit. It will approach channel capacity, because you really assume that there is no one, it's not one-to-one mapping. There always will be an error, but you can at least see how you approach. So that's kind of the idea. Okay, I'm still playing with the definitions, the ideas, but kind of was trying to summarize this for this presentation. So creative channel is sort of a error-prone medium that links between the agents, and there is this uncertainty or ambiguity, and there is a question of really how do you encode the voices so you can actually create a good communication. And this is still an open question, and I probably will not get to that specific question of lossy coding today, but I will see. I might continue next week or 2 weeks from now, depending on what the plans for next week will be. All right, so we did some initial work, and I think that's what Vinesh probably presented before, when we tried to measure mutual information between two voices. Okay, and then instead of mutual information, we want to do this transfer entropy. So the transfer entropy, we derived a specific measure of this transfer entropy based on so-called information rate or predicted information. I will not really go into this way of us estimating the transfer entropy. This is symmetric. It's voice A and B and to A, so it's kind of both ways. But kind of what we derived for this symmetric transfer entropy was really that the interaction or the causal influence of each voice on the other voice. And causal, I mean in the sense that the past influences the next step of the other voice without, or when the dynamics of that voice was taken into account or kind of canceled out by conditioning. So each voice is an agent, improvisation is listening and playing, you have information passing between the agents. I will not talk about the reduced representation today, but overall it was kind of this expression that showed that you have some kind of a mutual information between instantaneous values. This is kind of mutual information that doesn't take into account the past. And you have the predictability of the information rate of each voice. So in some sense, you can measure the interaction between two voices by looking at how predictive or how much information is passing from the past to the future on the joint pair, C and X. Okay, one is the conditioning, one is the output. Okay, so this is between the next prediction in the past. So you have kind of how much information rate is on both voices together, minus the information rate or how predictable individual voice X is, how predictable individual voice C is, and their instantaneous mutual information between C and X when the past is not taken into account. The past here is this marked by this line on top. So this is not really kind of slide which is not really related to the flow of what we're doing, because we're going to estimate this, the transfer entropy in a different way. But that was kind of the motivation that in some sense, polyphony, if you think about the rules of, music school, at least, when I was told what is good polyphony. Well, the good polyphony is that actually every voice can be independent. Basically, you can sing every voice as a complete musical piece without considering the other voice. So it has a lot of its own unfolding information, that predicts itself. But then also, when they join together, they kind of flow nicely together. So the marginal influence between them is really how nicely they flow together, minus how nicely each one of them flows, and some kind of mutual information between the two. Okay, I don't want to. We're almost an hour now. So for trying to kind of find more principled ways of defining this work, we've been looking into this second paper that I also put in the folder, which is this one, data-driven optimization of discrete information over discrete alphabets. Really, information theory paper has nothing to do with music or agents, okay? And we're kind of looking into this specifically for estimating so-called directed information. So when I'm saying transfer entropy and directed information, I pretty much mean the same thing, okay? Let me see. Okay, let me just skip a few slides. Okay, yeah, so we're talking about mutual information estimators, okay? So what is a mutual information estimators? We said it's the mutual information in X and Y. So there is something called MINE, okay? I will not kind of go through this right now. MINE is actually estimating mutual information when you have no memory, okay? You don't have any dynamics of each of the sequences. You basically have a lot of independent samples. They have some kind of a joint probability, and you want to estimate this joint probability. So MINE is actually a very powerful way of estimating mutual information using deep learning. Before that, like a very classical estimator of mutual information was called the Kraskov estimator. I don't have Wolfram notebooks, so I cannot show it, but you can download and see. This is just an example of how it estimates the mutual information. Actually, you have X and Y, so you have two variables. They have some kind of distribution, okay? And what you do, you basically cut it into slices, boxes, and then you basically calculate the mutual information. You have the marginal information, so it's entropy of X, entropy of Y, entropy of X and Y together, and you just use these equations. You kind of run this through different, it kind of adaptively chooses the sizes and really does it by the book. It actually estimates the entropy of X, entropy of Y, and entropy of X and Y together, and uses the expressions of mutual information to estimate. So this is kind of very straightforward. But instead of this, what MINE does, it actually learns some kind of a neural network that maps between X and Y, and it keeps training this network. And once it converges, it actually gives you much better estimator of mutual information. So this is for memoryless channels. Once you want to use something that has memory, mine becomes dyne. Okay, so this is the whole dyne idea here. Okay, and this is why we were looking into this paper, because the authors of this paper actually proposed an extension of mine into dyne. So instead of mutual information neural estimator, we have, sorry, directed information. So DI is for directed information neural estimator. It wasn't really adopted yet in the machine learning community so much, but they actually proposed it and used this for this channel coding thing. Okay, so this model, in some sense, is something that we're considering to adopt for improvisation. Okay, not so much the code itself, but this conceptual model. Okay, so let's review this once more, and then I'll probably wrap it up for today. So what we have here is really, we have a generator, okay, which let's say is our agent, okay. This agent generates access, okay, and then you have a channel. The channel actually is the response. What the channel produces is actually the musician hears X, okay, and it now plays Y, okay. Now it plays Y, but it also played previous Ys, okay. The uppercase, sorry, the upper, yes, with subscript and upper scripts, okay. The T on top means that these are sequences from all the past, whatever, from 0 to T minus 1. So this is all the past up to T minus 1, all the past of Y up to T minus 1, and this is the next output of Y, okay. So the Y depends on the past of X and on its own past. So this is what the channel represents. This is really how the musician will generate its response. Of course, we don't know the channel. That's his own, whatever, his own mind or his own brain, whatever makes him take into account his own music and the music of the other musician, okay, or the agent, and respond to it, okay. Now, what we want to do is, in some sense, tune the generator, okay, in a way that will have maximum information or maximum directed information between X and Y, okay. So to do this, we actually want to be able to estimate the directed information between X and Y, okay. So the question is how we train, or what we do, what model we have here to tune dyne, okay. So there is this loop here which trains the direct information. This is trains in a sense, it estimates it, but it estimates it by training a network here. And then it uses this loss as a signal, okay, to fine tune the generator. Now, in this case, it's really done using policy optimization. So there's a reinforcement learning step here that kind of takes these examples and fine tunes the generator. Okay, so we have basically two steps, and the analogy, I think the best one, explanation I heard about this was thinking about this almost like a GAN. Okay, this is like a discriminator, and this is the generator. Okay, so you train the discriminator. Okay, and in this case, it's not discrimination, it's really maximizing the interaction. Okay, so you have this phase of like a critic, okay, that learns the data. And then you have basically the actor or the generator that's being updated. Okay, so this is kind of almost like generalizing GAN, but instead of false or fake or true, okay, a discrimination, which in GAN we actually can kind of plug in and we know exactly what goes on there. So the discriminator actually learns something which is well defined. Here we have a discriminator which basically just tries to optimize its own estimation of how X and Y are related, okay? And with this estimate, it creates signal that now will train the generator. So there's two steps, the the critic or the discriminator is trained, and then the generator is trained, and the critic is trained, the generator is trained. And in this way, you kind of try to fine-tune your generative model so that it will maximize the interaction between this model and a musician, where we can assume or model that interaction as a channel. Yeah, so this is some details from that paper. Maybe we can look at this more in detail some other time. But actually map, this directed information optimization into Markov decision process. So this is how they use reinforcement learning. So the states are the past of, the output and the past of the input. The action, okay, is actually the next input that is being generated or produced, okay, and then it goes through the channel and it creates an output, and the reward is really the directed information. Okay, actually it's they're very mathematical, so to be exact, the reward is some expectation up to time t, and then you average over all possibilities and you get this directed information. But actually, this is kind of their formulation that says that the directed information rate optimization problem is infinite horizon average reward Markov decision process, where the objective is the directed information. So with all of these equations, okay, without really proving anything, we're just saying that we have some theory to borrow here. Basically, what we are saying is that our goal, okay, we can think about the directed information as a reward signal, as a reinforcement signal, and with this signal we can fine-tune the generator. Okay, and that's actually an idea that we were exploring even before we have found this paper or talked to these people. We're kind of playing with the idea of using the transfer entropy or the directed information as a reward signal to fine-tune a generative model. So I think now we kind of have a little bit more of a theoretical foundation for this approach. And I would say, just as a summary for now, I think it kind of broadly falls under this problem of control and adaptation of pre-trained generative models. Because what we want to do is really take like a transformer, a musical transformer. So in this case, we'll start with some kind of pre-trained generator, okay? And we want a musician to interact with this generator, and we'll see what musical responses will be. Then we'll kind of estimate their interaction and then fine-tune the generator. So this whole idea of learning the generator, in the original channel capacity problem, they were actually trying to learn the generator from scratch. In our case, we want to use an existing model and fine-tune it. So that kind of falls under this approach, which is very, it's a hot topic in language models. Okay, we still don't have this so much in music transformers. Okay, we're talking about doing conditional transformers, controlling transformers. So at least in the language models, they have these techniques, prompting and fine-tuning, and then the human feedback reinforcement learning, or some people call it HFRL, some people call it RLhF. So the base model is really pre-trained using some continuation criteria, kind of self-supervised, to predict the next continuation of the signal. Then when you want to interact with ChatGPT or with Music Transformer, you provide some conditioning labels, okay, some tokens in the beginning, or context and melody, and it will hopefully generate a continuation. Okay, now at least in ChatGPT, there are techniques to provide the context in a specific way. I don't know, you assume a role, okay. We kind of prompt the model to look into some kind of subspace of the language generation you can do. So that's kind of all these kind of prompt engineering ideas. So you start you kind of initialize the model with some prompts, and then you continue your generation from there. Okay. There is fine-tuning, which is really retraining the model or updating. It's kind of transfer learning, that you do something to change either the weights of the language model, or maybe weights of some of the final layers of the language model, to include additional knowledge. That's kind of adaptation to new domains. Okay, so you can do fine-tuning. So that kind of improves the performance of the model for specific tasks. But apparently it's not enough. And then you also have this human feedback reinforcement learning, where you have you actually train some classifier based on human judgments of the pairs of input and output. Okay, and apparently with fine-tuning, and this is kind of a paper that compares these different ways of adaptation or fine-tuning of language models. It shows that fine-tuning actually, a small model, this is the size of the model, 1.3 billion parameters. We don't have such huge models in music, but a model with fine-tuning of 1.3 billion parameters works better than an untuned model, base model, with 175 billion parameters. So there's something interesting about the fine-tuning, the actual interaction between human and the machine, that actually just training this on other data and more data, and fine-tuning this maybe on something outside of the data, is still not good enough when we talk about interaction. And there is some need of actual interaction with the humans. So what we think we can propose is some sort of an alternative, instead of like thumbs up and thumbs down, which is the way the RLHF is working, and have some way of just rehearsing with the model that will do this kind of human-based fine-tuning. So I think this will be the last slide. So kind of in language model, the fine-tuning is really done in a way that you roll out your basic model, right? So you have the query and the response. That's the basic LLM that does it. But then you do this training on the human response, the human reward. Basically, you take the pairs of the query response, basically, only you say, okay, I'm taking now the pairs, the performance with the the joint performance between the human and the machine. Here it's query and response. And then I look at all of these pairs, okay, I look at all these performances together, and I judge them as a human, whether they're good or bad, okay? And then you train a reward model. You basically train a classifier, okay, that learns somehow on these pairs of query and response, or the pairs of the performances, which are good and which are bad. And then you have this reward model, okay, that you can plug into this PPO. PPO is the policy optimization, one of the methods where you basically have to keep two copies. You have your reference LLM, which keeps some of the knowledge of the LLM. Actually, you have to have it there so you don't forget everything. You don't really recopy the query to the response. And then you have a new LLM that you update, where you basically use this reward model to kind of run this optimization. So that's kind of the overall strategy that I'm kind of proposing, or we're working on, and we're thinking about. But from here to the actual system, we still have a lot of work to do. I think I'll stop the sharing right now, and if you have any questions.
Yes. Yeah, so can you go back to the slide?